Hey, Chemgal here. In this video, we're going to clarify stereoisomers, enantiomers, and diastereomers. We're also going to discuss chiral centers and R&S configuration. Yikes, that's a lot of big words, but I promise it'll make sense by the end of this video. So, what's a chiral center? An easy way to think of a chiral center is an atom that's attached to four different things. So below, for instance, I have this carbon here highlighted in red, and we see here that it's attached to an alcohol group, a hydrogen, a methyl group, and an ethyl group. These are four different groups, and so we say that this carbon over here is chiral, or it's a chiral center. What about the example I have to the right? This carbon here is attached to an alcohol group, a hydrogen, and two methyl groups. So, because these two groups are the same, this carbon isn't attached to four different groups. And so we say that this is not chiral. In other words, we can also say that it is achiral. Why does this matter anyways? It's because the groups attached to the carbon are going to orient themselves in different directions around the atom, and the direction in which they orient themselves actually matters a lot. So let's examine this chiral center a little further. Here I have the chiral center redrawn, and you might see it being drawn with wedges and dashes, as in these examples here. Remember that these are 3D structures, so the wedges here indicate that the group is actually pointing towards you, while the dashes indicate that the group is actually pointing away from you. If a group is on a straight line, as in this carbon chain here, for instance, that means that it is in the plane of the page. If we want to talk about which direction the groups are going in, we use something called R&S configuration, where R is clockwise and S is counterclockwise. Let's see what we mean by that. So to label the direction, we look at the atoms branching out from the chiral atom. So in this case, branching out from this chiral carbon here, we have oxygen, hydrogen, carbon, and this carbon here. And so we start off by assigning priority to the heaviest atoms closest to the carbon here. So we ask ourselves, who's heavier? Oxygen, hydrogen, carbon, or carbon? Remember that oxygen has an atomic mass of 16, carbon has an atomic mass of 12, as in this case is here, and hydrogen has an atomic mass of 1. So we're going to give oxygen priority number 1, and so now we gotta figure out who's gonna get priority number 2. Well, we know that this carbon and this carbon both have an atomic mass of 12, so who gets second priority? Now we gotta ask ourselves, what groups are these carbons attached to? So this carbon here is attached to 3 hydrogens, whereas this carbon here is attached to 2 hydrogens and another carbon. And so we see over here that this carbon is bonded to a heavier atom in addition to its 2 hydrogens. Therefore, it's going to get priority number 2. So by default, this group gets priority number 3 and hydrogen gets the least priority of priority number 4. So now what we want to do is follow the direction of rotation. So you go from 1 to 2 to 3 to 4. And so we see that we are going in the direction of a clock, clockwise. And so we say that this group over here is going to have R configuration. Now, I want to mention that in order for this naming system to work, the hydrogen must be on a dash as it is here. So let's see, for instance, what might happen when hydrogen is not on a dash. So in this case, hydrogen is on a wedge. So what happens here? Well, let's go ahead and assign priority from the chiral center. We know that this oxygen is going to be the heaviest, then this ethyl group, then this methyl group, and then this hydrogen. So now if we go in the direction of these groups, we see that we are also going clockwise. And so you might think that this is also R, but that's not correct. Because remember, I told you that the hydrogen must be on a dash in order for this system to work. But here it's on a wedge. And so what that means is we have to reverse the direction. And so if we reverse the direction, we see here that we're actually going to be going counterclockwise. And so that means we're going to be going in the S direction. And so we say that this chiral center is S-configured. So as a recap, when your hydrogen is on the dash, you can keep the direction as is with the numbers. And when the hydrogen is on a wedge, you must flip the rotation, like so. And so to differentiate between these two structures, chemists use the R&S system when naming too. So you might see this over here as R2-butanol and S2-butanol. You might also see these being written as R-butan 2-ol and S-butan 2-ol. One more thing about chiral centers is that they're said to be optically active, meaning that if a beam of light hits a chiral molecule will shift the light's axis of rotation. Although I don't think you'll be expected to know too much about that, but you could just be aware that chiral means optically active. And so now you might be wondering about the relationship between these two guys. So you notice how they have the same connectivity where these atoms are attached to the same groups. However, they have different rotations about their chiral centers. And so because they have opposite rotations around their chiral centers, we actually have a special name for these guys. That these guys are called enantiomers. Again, that's when you have compounds that have the same connectivity but opposite rotations around their chiral centers. So for instance, this guy has an R clockwise rotation and this guy has an S counterclockwise rotation, while these atoms are attached to the same groups. Let's talk a little bit more about enantiomers. And so now let's say your professor gave you this example and told you to draw the enantiomer for the following compound we have here. First, we got to ask ourselves, how many chiral centers does it have? So take a moment to pause the video and figure out which atoms here are chiral centers. And so if we go along this carbon chain, we might ask ourselves, is this carbon here a chiral center? And we see that it's not because it's attached to 3 hydrogens. And that means that it's attached to 3 of the same groups. And a chiral center has to be attached to 4 different groups. So this carbon is not a chiral center. And what about this carbon? Well, we see here that it's attached to a methyl group, this carbon here, this alcohol group, and we also have a hydrogen here we haven't drawn in. So because this carbon's attached to 4 different groups, this carbon over here is definitely a chiral center. Let's go ahead and call that chiral center letter A. Now what about this carbon here? Is it attached to 4 different groups? Well, we see here that it's attached to a chlorine. There's a methyl group over here. There's this carbon over here, and there's a hydrogen we haven't drawn in. We see that it's attached to 4 different groups, and therefore this carbon over here is a chiral center. And we call that chiral center letter B. Now what about this carbon over here? Again, attached to 3 of the same groups, hydrogens. Therefore, it cannot be a chiral center. Oxygen isn't attached to 4 different groups, and neither is chlorine, so these guys can't be chiral centers. So we got 2 chiral centers over here, and I'm going to write them down, chiral center A and chiral center B. So now we want to assign whether they are R and S. Draw in those hydrogens so we can do that. Now take a moment to pause the video and assign configuration for chiral center A and B. So let's start with A here. We see that this chiral center is attached to an oxygen, a hydrogen, a carbon, and a carbon. Remember, we're not looking specifically at the groups. So we're not saying it's attached to an alcohol group and a methyl group and whatever this thing is, right? We're saying which atoms is it attached to. So it's attached to an oxygen, a carbon, a hydrogen, and a carbon. So who's going to take priority number 1? Oxygen is going to take priority number 1 because it is the heaviest. Now who's going to take priority number 2? We have 2 carbons here. And so they got to battle it out to see who's the heavier carbon. Now this carbon's only attached to 3 hydrogens, but this carbon over here is attached to chlorine and another methyl group. So this guy is definitely going to be the heavier group, and it's going to take priority number 2. That means that this methyl group is going to take priority number 3, and that leaves hydrogen with priority number 4. And so now if we map out the direction of priority, we see that we are going in a clockwise direction. And so that means that we are going to have an R configuration here because we are going clockwise. And clockwise means that we have an R configuration. So we can go ahead and write that in. Chiral center A is going to be R. Remember, we were able to do this because the hydrogen was on a dash. Otherwise, we would have had to reverse the rotation. Now let's try chiral center B. Chiral center B is attached to 4 different groups. But who's going to have priority? Is it going to be this chlorine, this hydrogen, this carbon, or this carbon? And so chlorine is going to take priority number 1 because it has an atomic mass of 35. Now, you don't need to freak out about these numbers, and you don't need to know the exact number, but you can recognize that a halogen like chlorine is going to be way heavier than a carbon or a hydrogen. So it's going to take priority number 1, and now we can assign priority number 2 to either this carbon or this carbon. And this carbon on the left is going to be way heavier because it's attached to a whole lot more things. So that's going to get priority number 2. And therefore, this methyl group is going to get priority number 3, and this hydrogen is going to be stuck with priority number 4. And so if we map out the direction of rotation, we see that here we are going in, again, a clockwise direction. I know I used to get confused by this, so if you ever need to, just think about the direction that a clock goes in. And so we know that this is going to have an R configuration. So we can go ahead and write that in there. And so we see here that both these chiral centers are going to have R configuration. Now, what does that mean about its enantiomer? Remember that I told you that an enantiomer has the same connectivity, although its rotation about the chiral centers is exactly the opposite? So if over here I have my chiral centers are RR, my enantiomer must have chiral centers that are SS. So I have to make sure that when I draw my enantiomer, I draw it with both chiral centers having an S configuration. And there's actually 2 ways to do this. So below here, I just have redrawn the compound that we had up here. And we know that these chiral centers are RR. So for the first method, you know that you can redraw the compound as is and reverse the rotation about the chiral center by drawing it on the opposite. So for instance, this alcohol here was on a wedge, so if we want to reverse the rotation on the chiral center, we should just draw it on a dash. And if this chlorine here is on a wedge, we can reverse the rotation for the chiral center by drawing it on a dash. And if you don't believe me, go ahead and try to calculate the configuration for both of these chiral centers, A and B. So remember we said that we know that both these chiral centers, A and B, are RR. Therefore, these chiral centers over here must be SS. So let's go ahead and letter those accordingly. And let's go ahead and make sure that these two guys are SS. We can draw in the hydrogen groups in order to calculate chirality. So let's go ahead and do it for chiral center number 1. We know that this oxygen group is going to get priority number 1, this carbon's going to get priority number 2, this methyl group's going to get priority number 3, and this hydrogen is going to get priority number 4. So for chiral center letter A, we're going in this direction. But remember that this hydrogen right now is actually on a wedge. And what are you supposed to do when the hydrogen is on a wedge? You are supposed to reverse the direction. So that means that we have to go in the opposite direction. And so right now, we are going counterclockwise. And so if we're going counterclockwise, that means that we are going in an S configuration. So this guy right over here is S. And let's go ahead and calculate it for the second chiral center. So if we're looking at this chiral center, this chlorine's going to get priority number 1, this carbon's going to get priority number 2, this methyl group's going to get priority number 3, and this hydrogen's going to get priority number 4. So now we go in the direction of priority. And because this hydrogen over here is on a wedge, that means that we got to flip the rotation. And so that means that we're actually going in a counterclockwise direction again. And does that mean that we are R or S? Because we're going counterclockwise, we have an S configuration yet again. So we see here that an easy way to draw the enantiomer for this compound is just by switching the wedge and the dashed positions. So because this alcohol group was on a wedge, I could just draw it on a dash, and that's going to flip the first chiral center from R over to S. And for the second chiral center, the wedge had a chlorine on it, but I redrew that chlorine on a dash, and that flipped the chiral center from R to S. So it's actually easy peasy. Now remember I told you that there's another way to do this. So let's go ahead and try it for the other. So now I went ahead and redrew in that this chiral center here is going to be RR, but we already knew that because we calculated it above over here. This is called the mirror method. And so what you want to do is draw a dashed line here and imagine that there is a mirror in front of this compound. What might its reflection look like? And so if this guy were to stare at itself in front of a mirror right now, it would look something like this. So if this guy were standing in front of a mirror, it would see its reflection. And so you might be wondering how the configuration flipped here. And that's because this chain actually inverted. So let's go ahead and calculate the new chiral center configurations. So we initially called this chiral center A, and we called this chiral center B. Now we have to be careful when reassigning the chiral centers, because the group that had the chlorine on it was chiral center B. So that means that this group over here is also chiral center B. So this carbon is going to be chiral center B. And that means that this carbon over here is going to be chiral center letter A, because it corresponds to the chiral center that had the alcohol group. So we have chiral center A and B. Let's take a moment to draw in our hydrogens. So for this chiral center A over here, who's going to have the highest priority? Is it going to be oxygen, hydrogen, carbon, or carbon? And by now you should know that oxygen is going to have priority number 1. These two carbons got to battle it out for priority number 2. So this carbon over here is going to get priority number 2 because it's attached to heavier groups than this carbon. And so now that leaves this carbon with priority number 3 and this hydrogen with priority number 4. And so if we map out that direction of priority, it's going in the counterclockwise direction. And that makes sense because the hydrogen here is on a dash, so we can keep that direction. So if we're going counterclockwise, that means that we are going to have an S configuration here. Now let's go ahead and see what chiral center letter B is going to look like. So now this chiral center over here is attached to this carbon, this chlorine, and this hydrogen. And so who's going to get priority number 1? And by now you should know that chlorine is going to be the heaviest, so it's going to get priority number 1. This carbon is going to get priority number 2 because it's attached to a lot more heavier groups than this carbon, which is going to get priority number 3. And then this hydrogen will be left with priority number 4. Remember that hydrogen has an atomic mass of 1, so it's usually always going to be group number 4. So now if we map out that direction, we see that we are going in a counterclockwise direction yet again. And so counterclockwise means that we have an S configuration. So this is going to have a configuration of S. And so now we see here that we've successfully drawn the enantiomer for this compound by drawing its mirror image. And that's because the chiral centers flipped from R to S, while maintaining connectivity to the same atoms for each chiral center. So as a recap, there's 2 ways to draw an enantiomer for a compound. You can either draw the compound as is and invert their chiral centers so whatever's on a dash becomes a wedge and vice versa, or you can draw the mirror image for the compound, which means inverting the chain like so. And if you do this, you gotta keep the groups the same. So if this alcohol group is starting off on a wedge, it's gotta stay on a wedge. Like with this chlorine, it started off on a wedge and it stayed on a wedge. And inverting that chain is what's going to rotate the direction from R to S and vice versa. So now here's the thing. There can only be one enantiomer for a compound. So knowing that, what do you think is the relationship between this compound and this compound? If they're both enantiomers to this compound, that must mean that they're both the same. And you might be a little bit confused about that. So let's go ahead and examine what I mean. I'm going to take these 2 compounds and draw them on a separate page so we can see how they're the same. So now here I have drawn for you the 2 answer choices that we got from before. And I want to take a moment to show you that these 2 compounds are actually the same compound. So let's go ahead and take a look at the first compound. So now here you could drop your pencil for a minute, and I just really want you to focus in on what I'm about to say. So now I want you to imagine that we have a y-axis here, and that we are going to turn this compound 180 degrees around this y-axis. What's that going to look like? Around, you're actually going to get this compound, and that's because what was originally pointing away from you on the dash is now going to be pointing towards you on a wedge. So while that chlorine was drawn on the dash position, now we see it here drawn on the wedge. And likewise for that oxygen, it was originally drawn on a dash, but now it's drawn on a wedge. And that's because when you physically turned it around the axis, the groups that were once pointing away from you are now pointing towards you. And so this is the hardest part about organic chemistry, is rotating 3D compounds in your head. And so you might need to use a molecular orbital kit to do this. Feel free to ask your teacher or your school library if you could borrow one of these kits. And so now we see here that these 2 compounds are exactly the same. As a recap from before, we got SS from both of these chiral centers, and these compounds have the same connectivity. So that's a key indication here that these 2 compounds are the same, just turned around. So whether you drew your answer like this using method number 1 or like this using method number 2, your answer choice is still correct. Now I want to take a minute to talk to you about these 2 enantiomers here. And so you might have heard another definition about enantiomers, that enantiomers are non-superimposable mirror images of one another. And that's correct. Enantiomers are non-superimposable mirror images of each other. So if we, for instance, look at these two mirror images, we can see that they do not perfectly superimpose. And that just means that these two guys over here do not perfectly overlap. So you see here that the alcohol groups are overlapping, but the chlorine groups aren't, and we have those extra methyl groups out on the side here. So they do not perfectly overlap with one another. And so that means that they do not superimpose. Therefore, these guys over here are enantiomers. So as a recap, enantiomers are mirror images that do not superimpose or overlap, as in this case. And so you might be like, whoa, hold up, aren't these two guys enantiomers? And yeah, they are enantiomers. But you gotta remember that if you draw the mirror image of this compound here, it's going to look like this. And that this structure is the same as this structure, just turned around. So technically, these two guys are still non-superimposable mirror images of each other. It's just that this guy is turned around, so we can't see that at the moment. Now, what if your professor told you to draw the diastereomer for the following compound? Well, what is a diastereomer? So you could draw a diastereomer of a compound by drawing the same compound, but by flipping one or more, but not all, the chiral centers configuration. And so what do we mean by that? So in this example, we only have two chiral centers. And we established before that both these chiral centers were RR. So if we wanted to draw a diastereomer for this compound, we would have to flip only one of its chiral centers to S. Now we said we can flip one or more, but not all. And so in this example, we can only flip one, because if we flip both of these chiral centers to S, then we would end up with an enantiomer. So that's why we can't flip all the chiral centers, because then we would end up with an enantiomer and not a diastereomer. And so an easy way to do this is to redraw the compound here and flip one of its chiral centers. So I'm going to go ahead and switch that alcohol group from a wedge over to a dash position. And if I do that, what happens to chiral center A? So because we switched chiral center A over from a wedge to a dash, its chirality will flip from R over to S. Now chiral center B stayed the same. It was on a wedge before and it's on a wedge now. So that means that it's going to remain as R. And so we see here that one of the chiral centers flipped. Before we had RR and now we have SR. So this is a perfect answer choice for drawing a diastereomer. We could have also approached this another way. So we could have redrawn the compound here and instead erased the wedge group from that chlorine and switched it over to a dash. And if we do that, we see that A is actually going to stay the same as R because it was originally in a wedge and it's still on a wedge, but B is going to flip to S because it was once on a wedge, but now it's on a dash. And so we flipped its chirality. And so here we went from RR to RS, and we only flipped one chiral center. So this is also another plausible answer choice for drawing a diastereomer. So now knowing that, we can go ahead and fill in the relationship for each pair of structures. Let's go ahead and try number 1 as an example to see how we might do this. So first off, let's label. We already calculated way in the beginning that this was RR. And now if we're looking at number 1, it's asking to fill in the blank for this example for the relationship between this compound and this compound, meaning are they diastereomers, are they enantiomers, or are they the same compound? So to do this, we can quickly look at their chiral centers, and we see that their chiral centers here flipped for both of them. While they were both on wedges before, now they're both on dashes. And so what does that mean? That means that both of these chiral centers are going to be SS. And so if we started off here with RR and we ended with SS, we know that both of these guys are going to be enantiomers. So we can go ahead and draw that in here as our answer choice. So for number 2 here, we saw that this first chiral center here flipped. And so if it was initially R, now it's going to be S. And we see that this chiral center over here stayed the same. So if it was initially R, it's going to stay R. So now, going from RR to SR, what's the relationship between these two structures? These two structures would be diastereomers. On to example number 3. Here we have this chiral center stayed the same. So if it was S before, it's going to stay S now. And because this chiral center changed, it's going to turn from S to R. And so the relationship between these two guys over here is going to also be diastereomers. And so now let's try number 4. So for number 4, we actually have SR going to RS. So we see here that this first chiral center flipped from a dash to a wedge, and the second chiral center flipped from a wedge to a dash. Now, what does that mean? Remember that I told you when both the chiral centers flip, they're going to be enantiomers, right? So if we real quickly wrote out A and B here, A and B, and we called this A and we called this B, and we called this A and we called this B, we see that A here was S and B here was R, and then A here turned to R and B here turned to S. So remember that the definition for an enantiomer can be when two molecules have the same connectivity but exactly the opposite rotations about their chiral centers, such as A flipping from S to R and B flipping from R to S. These are called enantiomers. So these guys are perfect enantiomers for each other. Now let's determine the relationship between the pair in number 5. So this is going from SR to SS. And so you know that that's going to be a diastereomer because only one of the chiral centers flips. So for number 6, we see that we're going from RR to RS. And so only the second chiral center is flipping. And so that means that we have another diastereomer. And so now I want to take a moment to classify all these terms. So a group of stereoisomers has the same molecular formula and the same connectivity. Enantiomers are a subgroup of stereoisomers that are mirror images of each other. And diastereomers are a subgroup of stereoisomers that are not mirror images. So what if your professor gives you a question like this? How many stereoisomers does this compound have? So throughout this whole video, we determined that this compound has one enantiomer, which we drew in 2 different ways, 2 diastereomers, and last but not least, the compound itself belongs to the same group of stereoisomers. So if we tally those all up here, we see that this compound has 4 stereoisomers. And so you might be wondering, if I have this question, am I going to have to draw all the enantiomers and diastereomers? And the answer is no, we actually have a shortcut for this. We use a special formula called 2 to the n, where n is the amount of chiral centers a compound has. So if I wanted to use 2 to the n to calculate how many stereoisomers this compound has, I would first have to ask myself, how many chiral centers does this compound have? And we know that this compound has 1, 2 chiral centers. So we can put in 2 for the subscript of n. And if we substitute 2 for the subscript of n, we get a value of 2 to the 2. And 2 to the power of 2 is 4. Therefore, we have 4 stereoisomers. So if you have this question here, how many stereoisomers does this compound have? All you have to do is count the amount of chiral centers in your compound and substitute that value for n, and that's going to give you the amount of stereoisomers that that compound has. So that's it for this video. If you liked it, please leave a thumbs up and feel free to subscribe. Happy studying!